Now here we're going to look at the t-distribution. The t-distribution is used when you have a smaller sample and you don't know your standard deviations, okay, your population standard deviations. So the University Data Center has two main computers. The center wants to examine whether computer 1 is receiving tasks that required processing times comparable to those of computer 2. So a random sample of 14 processing times from computer 1 showed a mean of 58 seconds and a standard deviation of 16, while a random sample of 15 processing times from computer 2 showed a mean of 52 seconds and a standard deviation of 19 seconds. Assume the populations of processing times are normally distributed and the variances are equal. These two bits of information are important. Whenever you go to deal with either confidence intervals or hypothesis tests for the z-test or the t, you have to be dealing with a normally distributed population. If it's not at least almost normally distributed, then you can't do either. You cannot do either a z or a t. So this is always something you've got to look for in the wording of the problem, that your populations are approximately equal, or normally distributed. And then when you have the difference, the two population means, then and the t with a small sample size, you need to know whether your variances are equal or not equal. Because if they're equal, then we can use pooled variances. If they are not equal, then you have to use non-pooled variances, which actually reduces your accuracy. Reduces, it enlarges your confidence interval and reduces your chances of rejecting your null. So construct a 95% confidence interval for the difference mu1 minus mu2. Okay, and complete the table, which is lower limit, upper limit. Okay, because our samples are small, both less than 30, and we don't know the standard deviations, we will use the t-test. Our test statistic is the difference of the sample means, which is 58 minus 52, so our sample means is 6. The difference of the sample means is 6. Okay? Since the problem states that we assume the variances to be equal, we will use pooled variances. The hard part of this calculation is finding your pooled sample variance. So here's the formula. See how there's a little p down here at the bottom? That is for a pooled sample variance. Variance is when we have the standard deviation squared. So it's important to note that this is a variance and it is a pooled variance. But all of these numbers are pretty familiar to you now. This is the size of sample 1 minus 1, so n minus 1, times the variance of that sample, plus the sample size 2 minus 1 times that variance, all divided by the degrees of freedom, which is n1 plus n2 minus 2. Okay? So your degrees of freedom is add your two sample sizes together and subtract 2. So this formula, of course, is given to you in the explain part of your ALEKS problem. So I recommend on these problems, I recommend that you print them out and make yourself a notebook. So you have your formulas, and then right on the actual notes, write how you go about solving these problems. So when we do one together, there's a lot of times I've found in the explain on the ALEKS that the explanation they give is just really complicated. I have found that to be true too often, that it's very complicated calculation or explanation for a not that complicated problem. So you might want to print it out and then come look at the supplemental session, or when you go to class, or when you ask your professor a question, or once you figure out how to work it out, take notes on these things so that you have a resource for when it's time to take the assessments or your final exam, which is coming up before too awful long. So just keep yourself organized, and you'll be able to you'll survive a lot better. Okay, so in our case, we're using the T, remember, and the margin of error, right, we're doing a margin of error, is T times, once again, the sample pooled variance times 1 over N1 plus 1 over N2, okay? So here is our margin of error. And so for this problem, X1 was 58, X2 was 52. The first standard deviation was 16, the second was 19. The first sample size was 14, the second was 15. Plugging all of that into the formula, for N1 minus 1 is 14 minus 1. S squared is 16 squared. 15 minus 14 minus 1. 15 minus 1 is 14, and then times 19 squared over 14 plus 15 minus 2. So, of course, you're going to subtract first. You're going to square the 16 before you multiply it times the 13. You're going to square the 19 before you multiply it by the 14, and then divide. And so note that the pooled variance is 310.444. Okay, so this pooled variance is 310.444. Okay. Now our alpha over 2, which is our significant our confidence level. Remember, alpha, our confidence interval was going to be 95%. So that leaves us 5% for the alpha. Over 2 leaves us 0.025. So T of 0.025, you can calculate, use the ALEKS calculator to find that. Remember, our degrees of freedom is 14 plus 15 is 29, minus 2 is 27. Okay, so now here's that same formula again, and we're going to plug in the numbers, T of 0.025. Remember that pooled variance was 310 times 1 over 14 plus 1 over 15 is, the T is the 2.052 times the square root of 310.44 times, and 1/14 plus 1/15 is 0.1381, and then that much is 6.54, so your margin of error is 13. So your lower limit is that difference with 6 minus 13.4345, which is negative 7.43, and the upper limit is 6 plus that same margin of error, which gives 19.43 for the upper limit of the confidence interval. Are there questions about the confidence interval for T? How do you solve for equations in brackets? If you're using your ALEKS calculator, I would just do this. I would do 1 divided by 14, and then make sure that you click so that your cursor is in the middle of that fraction and not still on the bottom. And now plus, and then do 1 divided by 15. So now I have the two fractions being added as whole fractions. And when I add that, I get 0.13809. Questions? When you do t of 0.025, let me do that again. So we go to the t, and then we put the 0.025 in the first blank. And your degrees of freedom was 14 plus 15 minus 2, so that's 27. And then that number just goes here into the the calculation.